I'm going to talk to you about search. Search is another fundamental problem in computer science, just like sorting. It takes on a few different sort of flavors or styles depending upon the context. In this case, when I talk about search, I mean we're going to be looking through something like an array or an array list to determine if a value is found in that collection. Now, there's a few different ways to do this. I'm going to cover two different ways, a linear search and a binary search. So let's start with linear search. So that means we're going to have some kind of target value. That's what I like to call it. Something we're looking for. So let's say the number 12. Now, I also have, let me draw out the array. My hand's not so steady tonight. Get a wobbly array. Now, I'm just going to throw some numbers in here. Just pick those totally arbitrarily. What linear search is a very simple algorithm. We're simply going to start at the beginning of the array and check each cell, each slot in the array until we find or don't find the value we're looking for. So we're going to start at the beginning. It's going to be, nope, not there. No. No. Just going to keep going down until, hey, this matches. So we'll remember true, and then we can just skip the rest. So we only need to go till we actually find what we're looking for. Alternatively, let me change this and change my array. Put in 8 again. We're simply going to, again, keep looking through each spot. One cell after another. And it's just false, false, false. So you think what we're really doing is, since arrays are indexed, I'm just going to use a simple for loop to accomplish this, right? I'm going to start I equals 0 and just keep incrementing it up all the way. I don't know, that was a weird way of writing that. I'm going to have I go from 0 to 1 to 2 and just check the value at I. So let me jump over to the code. That took longer than I wanted. All right. Now, it's quite simple. I have my main that's testing it. I called this contains. I'm simply accepting. In this case, I wrote this specifically for numbers, or for integers rather. My target I'm looking for. I'm going to set I is equal to 0, since that's the first index. I'm going to make the assumption we have not found what we're looking for. So often when we're doing a search, we want to assume we haven't found it. Sometimes we want to assume we do. In this case, I'm assuming we haven't found it, and I'm going to look for the item itself. So this loop condition is going to go until we either hit the end of the array or until we found the value. And that's all the if statement does. If the value at I matches the target, we're going to remember found is true. In either case, we're going to increment I. So as soon as we find it, the loop will be done. We don't need to keep looking anymore. If not, we have to go through and check every single thing in the array. Now if I go to run this, run the linear one. So it makes sense. I have two cases down here. Look for 20. 20 is in fact found. Look for negative 100. It is not. So let's go back to drawing board. So why is this called linear search? And you may have gotten this sort of intuition as I kind of go through and mark each thing. It's based upon the time. So again, we want to think, how long is it going to run? So again, we don't care about, well, since, computers change each year, right? Each year they get a bit faster than they were the year before. It used to be clearly they'd double about every 18 months. Now it's not quite as quick of a pace, but they're still getting faster. They still keep making better and better chips. So we want a way of expressing the runtime of an algorithm without tying it to a particular CPU. Because if we did that, then we couldn't compare our methods versus the methods they discovered, say, in the 1970s or the 1980s, because our computers now, our hardware, is just so much better. But the software, we've found better ways of doing things, but that's totally independent of the hardware. So as I've alluded to in my sorting videos, we need a more robust way of looking at the time. So what we care about, because things like CPU difference and because of differences in little programming choices, we want to typify if this is n, the size of the input, and this is time. We want to find a way of characterizing how long it takes. So if the real function for the time is 5n plus 38 or something like that, and that depends upon my particular Java implementation, what I really care about is just the largest term in the equation. So if this was going to, say t of n was going to kick out, the number of seconds or milliseconds or whatever it takes for my code to run based upon the size of the input, really we just care about how this scales. So that's why we say this is big O of n. So big O is a way of saying, well, we just want the most dominant term, because that's what asymptotically, as n keeps going up and up towards infinity, that's what's really going to dominate the runtime. And because something that takes n amount, this would be a linear function, hence linear search. And it makes sense if we just have a jumbled up array that, generally speaking, we need to look at everything there. We could get lucky. The thing we're looking at might be the very first item, but it could be the last, or couldn't be not there at all. So that's why we also look at, again, typically the worst case. Sometimes we consider average cases or best case, but we're typically considering the worst case. So that's what we care about. So this is big O n. That's why it's linear time. Can we do better than this? Well, let's scroll down. Let me I didn't give myself enough. Let me scroll up. Haha. So the alternative, something called binary search. Now, to do better than linear, we have to have some extra trick, some extra secret sauce, if you will. I don't know how this relates to sauce at all, but this, our different condition, that's a better way of saying it, is we need the array to be sorted. So I'm just going to throw in some numbers. 10, 14. Well, I said 14, but it looked like a 9. There we go. And let's say in this case, I have a target of, what do I want to find? Oh, how about 1? Now, what binary search is going to do, it's going to split, it's going to look in the middle. And since this is an even number, I'm just going to round up. So we're going to look in the middle and compare 1 versus 4. So this is going to, since 1 is less than 4, we can cut this in half and now only consider values over here. So I'll just duplicate it for sake of clarity. 2 gets its largest cell ever. Okay, great. Now, I'm going to look in the middle again. Aha, there it is. We have 1 versus 1. Goal, yay. I'll put equals here and put yay. We found what we're looking for. Now, let me rewind this with the different, but you can see, so this okay, example. Let me look for the value, let's say 8. So let's rewind. So we found that. So I'm going to go backwards. A lot of undos here. You're going to hear that nice clankety clank. I know you missed it. All right. Haha. Now, let's say I'm going to look for 8 in this array. Again, I'll find the midpoint. So I'll compare 4 versus 8. Well, 8 is going to be greater. Yeah, it's greater than sign. So that means we'll again divide this, and now only consider the top half. So I'll have, my art's definitely getting worse as I do this. I was hoping to get better, but well, sometimes things don't work out. Anyways, now we're going to compare again the middle. I'm doing kind of, if there's a tie or even number, we're going to go up 1. 8 versus 10. Well, it's less than. So we're going to take this again, divide it. I'll give myself a little more space. Oh no, I've run into my other stuff. Go away. Okay, now we're down to 4 and 8. Now I look in the middle, which is going to be here. So I have 8 versus 8. Got the equals. And we can say, I'll put a circle around it and go, yay. I could almost make a weird smiley face out of this. Anyways, we found it. So we searched till we found it. But the idea here was with binary search, fundamentally, is you look in the middle, and then if you haven't found what you're looking for, you cut it in half and you either go high or you go low. So here I went high, and then down here I went, so the first iteration I went high on it, right? Then once I determined 8 is less than 10, I went to the left or the lower side, and then continued my search there. So what would happen if I just run out? Well, you get down to a case like this. You go one further until you're just down to 1 cell, and if it's not there, you're just done. That'd be bad. That's sad. So you can maybe start to get the intuition why this is way, way, way faster. Let's jump over to IntelliJ. Now, what am I doing? It's right here. Clear all this. So here it is implemented. Binary search makes a lot of sense to implement as a recursive function. So let's go up here. I implemented it in a method named contains. It's going to, again, just like linear search, it's going to take that array of values and it's also going to take the target I'm looking for. Now, I'm using something called a helper method. Because I'm doing this recursively, because I want to pass in a couple extra values, I don't want to kind of expose that to whoever is going to use the contains method, so that's why I'm using this helper. So all the main method's going to, well, whoops, deleted, haha. All this is going to do is pass in starting values for each thing, which is, well, let's take a look. I'm still going to have the array that I need to look for. I still have target at the end, that are the values I'm looking through. The target is the thing I'm looking for. Low and high are going to be indices, because I don't want it, like when I was drawing it by hand, it looked like I was kind of copying things, or I was looking at smaller arrays. That's just sort of an illustration. I don't want to have to copy sections. That kind of defeats the purpose, and we'll slow this way down. So what I want to do is have these indices marking the high and low end. So as it runs, it will successively move those boundaries in. So the key to binary search, you got to have this midpoint. We want to look there. It's okay. This will probably arbitrarily pick the low end rather than the high end if there's an even number. What we're going to do is, this seems like a weird condition, but as those boundaries move in, if they cross, that means we've just run out of space. There's nowhere else to look. So we're going to return false in that case. That means we didn't find what we're looking for. If the middle value equals the target, success, we found it. If the middle value is less than the target, that means our target's larger. We need to move up. That is to the right, if you want to think of it sort of visually. In this case, all that means is I'm going to make the low point, the low point into the middle point plus 1. So you think we've kind of shifted everything over. And moving down is the same, is really similar. So if the middle value is greater than the target, that means we need to move down, that is to the left. So we keep the same low value, but we decrease the high by 1. And yeah, that's it. So it breaks down to this very nice recursive method. So let me just give this a run. Binary, so you can be convinced it works. So you can see in the first case where 10 is in the array, it's found. Or I'm looking for negative 10 and it's not found. Let me just print out so you can see what's going on. Printf. I'm going to do low. And this is also, by the way, a good debugging technique. So if I had a problem in here, this is what I would do to find it. Because often I tend to still make mistakes when there's indices involved and you're moving them by 1 or shifting those around. I usually think a bit more abstractly, so it's easy to be off by 1. It's such an easy mistake that computer scientists just call an off by 1 error. Anyhow, printing this out might make things interesting, so we'll do this. So we can see in the case of it finding it, it splits it in half. So the middle value, we have 0, 1, 2, 3, 4. Now, I'm looking for 10, so it's going to cut it in half here. So the middle value then, this is index 7, which will have 10 in it, so it finds it on the second go around. Here, we're going to I have a bug in mine. Let's replace this. So you can see this was actually doing it linearly. Now let's rerun this. Ta-da! I had to put mid here rather than high. If you just decrease it by 1, you're effectively doing this kind of weird linear search in one case. So remove my bug. See? It's a good thing to print it out. So I found my bug because it was working, but it wasn't working as I expected. And let me also put in mid value because this will make it a little easier to see. Or do values. Well, this might actually throw an exception, but we'll... Okay, good. We didn't do anything too weird. So what happened is when I'm looking for -10, it's going to look in the middle, which is value 3. Now it's going to consider everything below that. Looks in the middle values again, which it picked 0 because it went to the left instead of the right, like when I walked through it by hand. Now it's going to look at this. And then it goes through one more. So it makes the high go down to -1. So then it's just done because we get into this case. It's kind of interesting. Low minus. Oh, we just kind of got a little lucky because this ends up basically being 0, even when it's because it's 1 divided by 2. That ends up being 0 with integer division. So that's how I avoided that exception sort of accidentally. But anyways, we can see that it correctly goes, it has to go cutting in half and half and half, but it only takes 4 checks, right? Even in that worst case where it's not there. Now let's go back to this screen. So since we have this situation where we're cutting in half and in half and in half, sort of so we're going, from here down and down, right? Each sort of round of the search, rather than looking at each value individually. Since that's much faster. So it's the opposite of exponential, which would be doubling each time. We call it, well, that's kind of blurring it all together. We use log base 2, which we just write as lg of n. So that's log. So we use log n, which means basically the runtime grows very, very, very slowly. This is almost as good as you can get. So the cheapest would be what we call order 1. That means the runtime does not depend at all upon size of the input. So if I was going to draw a nice little graph over here, oh no, my art's getting successfully worse. This is linear. Log n is going to grow more like that. So I'll put a little n, I'll put a little lgn down here. Yeah. So that's the benefit of binary search. So this is now getting into real computer science. It's more than just programming. It's thinking about how exactly do we solve problems, what are the trade-offs, what are the advantages of taking particular approaches versus others. Binary search beats the pants off of linear search, but it has to have this precondition of has to be sorted, right? So if we do binary search on an unsorted array or unsorted array list, we're going to have a bad time. It's not going to work. So if we have this precondition of it being sorted, hooray, now search is much faster. But anyways, that's your introduction into searching and time complexity. Have a nice day.